Hello, welcome to sequence video number 4. We will be graphing sequences on a number line today, not on a coordinate plane, but on a number line. Let's look at the sequence we have here. This is a finite sequence a sub n, which is defined by the set of numbers 2, 4, 6, 8, 10. This is a finite sequence again because the range of numbers is limited. There are 1, 2, 3, 4, 5 terms. In our previous videos, we learned that we could make a recursive and an explicit function formula to come up with each term of the sequence. We also talked about that this is an arithmetic sequence because there is a common difference which each successive term of the sequence. Okay, let's look at the sequence and graph the sequence on a number line. Well, for my number line, I know that my numbers fall between 2 and 10, so I'm going to draw my number line here. Let's call this 0, and we'll call this 10, and so this will be 5. 1, 2, 3, 4, 5, 6, 8, 9, 10. Trying to keep my spacing adequate. So this term right here, this first term in the sequence, this is the a sub 1 term. The a sub 1 term is equal to 2. How are we going to graph this on this number line? Well, this is 2 right here. I'm going to say this is my a sub 1 term. And I'm going to say it's adequate to put a 2 underneath this a sub 1 marker here also. 4, that's my a sub 2 term. 6 is my a sub 3 term. Oops, wrote that backwards. 8 is my a sub 4 term. And then finally 10 is my a sub 5 term. Now for this number line, when we graph these sequences on a number line, we will not make sure all the time that our every number, let's say 5, would not actually have to be labeled on this number line. So real quickly, all we've done here is we've graphed the 5 terms of the sequence a sub n on a number line. And this is how I want you to graph this. Okay, let's look at the sequence that is defined by an explicit expression. A sub n is equal to 1 over n. Remember the n values we're using for a sequence are elements of the natural numbers or the positive integers. Therefore, we're going to substitute 1, 2, 3, 4, ... into this sequence. We're going to graph the sequence on a number line and see what happens. All right, I'm going to draw my number line here. And since the sequence is relatively simple, I'm not going to make a list or a t-chart of my n input values and my a sub n output values. We're just going to graph them right away on the number line. I'm going to start my number line at 0 because a sub n will not be negative because n is not negative. And then I'm going to plug in some values and see what n is going to approach, or what a sub n is going to approach. Let's let n equal 1. So a sub 1 is equal to 1 over 1. Okay, so a sub 1 is equal to 1, and then let's set n equal 2. So a sub 2 equals 1 over 2. Well, that's 1/2, which is smaller than 1. It looks like 1 is going to be our largest value, so I'm just going to end my graph at 1. And I know a sub 1 is equal to 1, so I'm going to plot that right here and call this a sub 1. We saw that a sub 2 is equal to 1/2. 1/2 is right here. This is a sub 2. That's equal to 1/2. A sub 3 is 1/3. Well, where's 1/3? Well, it looks like about right here. And it looks like each successive term is getting smaller, which means it's getting closer and closer and closer to 0. Let's see if that's true. Well, a sub 4 is 1/4, which is halfway between 0 and 1/2. A sub 5 is 1/5. Does that look like about 1/5? A sub 6, the sixth term is 1/6. And I think you guys see the pattern happening here. We have 1 over the term number, and the term number is getting bigger, which means the denominator is getting bigger. It means 1 over a bigger number is a smaller actual number. So a sub n, which a sub 7 is getting closer, a sub 8 is getting closer, a sub 9 is getting closer and closer and closer and closer to 0. That means that the rest of the numbers, a sub 7 through a sub infinity, seem to fall, means the output values seem to fall in this range of numbers. So the rest of my terms in my sequence will fall in this range. So I can write an interval for the rest of the terms when n is greater than or equal to 7, a sub n seems to be less than 1/6, greater than 0. So the rest of my terms, when n is greater than or equal to 7, or we could just say greater than 6, the rest of the terms fall in this range of numbers, which written in interval notation would be, well, we don't know if it's going to get to 0, so we're going to use parentheses 0 to 1/6. We're not going to include 1/6 also. So what does that mean? Well, all the terms, rest of the terms, well, we have infinitely number of terms fall in this range of values. And it seems like our numbers are getting smaller and smaller and smaller and approaching 0. That seems to tell me that as n goes to infinity, a sub n seems to approach 0. It means a sub n, the range, the terms in the sequence, get closer and closer and closer and closer to 0. Now we will define what's happening here, what's happening to the sequence as n gets bigger and bigger and bigger and heads towards infinity. We will define what happens to a sub n as it approaches 0 in a more specific terminology in some later videos. But in general, look at the sequence. The sequence is an infinite sequence because we can plug any value in for n to find any term number. As this sequence increases, as the terms increase, the sequence heads towards 0. It gets close and closer and closer to 0. Now let's take this sequence, a sub n equals n over n plus 1. Let's graph the sequence on a number line and see what value this sequence heads to, the terms of the sequence get towards as n increases towards infinity. Okay, number line. Well, we know our lowest value can be 0. A sub 1, that's equal to 1 over 1 plus 1 is 2. Okay, A sub 2, I'm just going to make a couple of, see what some of the range is going to look like so I can know how to number my number line. A sub 2 will be 2 over 2 plus 1 is 3, so 2/3. A sub 3 is equal to 3 over 4. Well, it kind of looks like a pattern is happening here where the numerator is always 1 less than the denominator. You should see that from this expression up here. A sub 4 would be 4 over 5. And then A sub 5 is equal to 5 over 6. Well, if you're wondering how to divide up your number line here, well, let n equal 10. That'll be 10 over 11. Let n equal 12. 12 over 13. Well, it looks like our top value might be 1. Let's graph this sequence on this number line. A sub 1 is equal to 1/2, so here's about 1/2. A sub 1, that'd be 1/2. A sub 2 looks like 2/3. Okay, about right here. A sub 3 is 3/4. Well, hopefully you see what's happening here. As n is getting bigger, A sub n is getting closer and closer and closer to 1. A sub 4 is 4/5. Let's say about right here. A sub 5 is 5/6. Then A sub 6 would be 6 over 7. Check here. A sub 7 would be 7 over 8. So on and so forth. What about A sub 100? Well, that's going to be 100 over 101. Closer and closer and closer to 1. The difference between these values, the one piece that's missing is getting smaller and smaller and smaller from the complete whole 101 parts. The one piece that's missing is smaller. If I have A sub 1,000, that piece is even smaller, so it's getting closer and closer and closer to 1. So it looks like for this sequence, as n gets bigger, heads towards infinity, the sequence itself, A sub n, seems to head towards 1. Means all the terms of the sequence are getting closer and closer and closer to 1. Now, like in the previous problem, can I write an interval where the rest of the terms that are greater than 5 or greater than or equal to 6 lie? Well, if n is greater than 5, it looks like the terms A sub n will be less than 1, but greater than 5/6. So the interval which the remaining terms would fall in would be from 5/6 to 1. The rest of the terms of the sequence fall in this little area. It seems kind of funny how the first 5 terms took up this much of the number line, and infinitely many terms, the range of the n values as n goes to infinity, falls in this little area. We will later define this little area as being maybe like a neighborhood of this sequence, and we'll get into more of a proof, and then we'll define this a little bit better. Okay, let's take a look at this sequence. A sub n equals 2n plus 1. This sequence looks a little bit different from the previous two. Let's see what happens. Number line, let's see, A sub 1. Well, that equals 2 times 1 is 2 plus 1 is 3. A sub 2 is equal to, that'll be 4 plus 1 is 5. A sub 3 is equal to 7. A sub 4 is equal to 9. A sub 5 is equal to 11. Well, if we graph these on a number line, we can see pretty clearly that, well, here's 0. Well, these terms keep getting bigger and bigger and bigger and bigger, and it seems like they don't have a limiting factor. It seems like they don't go towards a number. It seems like they just keep getting bigger, and well, you add 2, you add 2, you add 2, from this multiplying by 2, then plus 1. We talked about that a little bit in some previous videos. Well, A sub 100 is equal to 201. So it looks like this sequence increases, the terms increase without bound. That means as n goes towards infinity, a sub n goes towards infinity. That means all the terms of the sequence start heading towards infinity. The terms of the sequence, the ranges of the sequences gets bigger and bigger and bigger. Well, we can graph this on our limb line also. Well, just be, let's say here, 1, 2, let's say this is 3. That'd be a sub 1 is 3. 1, 2, the a sub 2 would be 5, and then a sub 3, 7. A sub 4 is 9. A sub 5 is 11. So as these terms, as n gets bigger, the sequence gets bigger. It does not head towards a value. The sequence increases without bound. Here's an interesting looking sequence. Looks like we have -1 to the n power times 1 over n. Well, we looked at what happened if the sequence was a sub n equals 1 over n. But let's see what this does to the sequence. All right, let's let n equal 1, 2, 3, 4, 5 like we did in previous examples. So when n equals 1, a sub 1, well, that's going to equal -1 to the 1 power is -1. 1 over 1 is 1, so -1 times 1, that's -1. Let's change the size. There we go. A sub 2, maybe we'll change it back. There we go. A sub 2, all right, -1 squared, and when -1 times -1, that's +1. So 1 times 1 over 2, that's just 1/2. A sub 3, 3 factors of -1, that would be -1. -1 times 1/3 would be -1/3. A sub 4, 4 factors of -1, that would be +1 times 1/4. And then finally, a sub 5, that would be -1 over 5th, 1 over 5. Graph these terms on a number line. By inspection, we see here, well, we got -1, 1/2, -1/3, so that number gets closer to 0. Then from the positive side, we have 1/2 to 1/4, so it looks like these numbers are getting smaller also. So it looks like I can create some boundaries here. 0, -1, +1, and then I can actually graph this sequence. It looks like we're going to approach 0 from both sides to see if it's true. Okay, -1 is a sub 1. 1/2 is a sub 2. A sub 3 is -1/3. Well, it's about right here. We're back on the negative side of the number line. A sub 4, 1/4. Positive, but closer to 0 now. Notice that the even n values are on the positive side. The odd n values, the output is on the negative side. A sub 5 is -1/5. We'll call this about right here. Now it looks like as n increases, well, a sub 6 would be here, a sub 7 looks like in here, a sub 8 looks like in here. Looks like we're alternating around 0, but we're getting closer and closer and closer and closer and closer to 0. Well, it looks like in this sequence here, as n goes towards infinity, it's like a sub n approaches 0. Now we could write an interval for which the rest of the terms of this sequence for n equals 6, 7, 8 on out into infinity, well, all those numbers, infinitely many numbers, terms of that sequence will fall within this range of numbers from negative 1/5 to positive 1/4. Infinitely many terms of that sequence will be in this amount of area. So the rest of the terms will fall in the interval negative 1/5 to positive 1/4.